Okay, this is lecture 12 of basic calculus 1. So, recall that we had discussed continuity, that is continuous functions and some algebra of continuous functions. So, today we will be discussing one result, specific result, and then some of its corollaries, which are themselves very important results on continuous functions, and solve some problems basing on those ideas. Okay. So, the main theorem here is the continuous image of a closed bounded interval is a closed bounded interval. That is our main result. We will not prove this result. In fact, it requires the completeness principle and some rigorous analytical tools to show that this really holds. So, what it says exactly is this one, though you remember in this form that the continuous image of a closed bounded interval is a closed bounded interval. So, actually it means this. Suppose D is a subset of R, it is a some set of real numbers, and you have a function defined on this D taking real values. That function f, let it be continuous. And let us choose any closed bounded interval which is a b, a is less than or equal to b. We will really take a less than b, because equal to b will give a singleton. So, a is less than b, that is assumed here implicitly. Let us take one closed bounded interval and which is a subset of D. So, that means D is such a set which contains at least one closed bounded interval. Of course, we are only interested in defining continuous functions on intervals or unions of intervals. So, this assumption is not a big thing for us. So, suppose D contains such a closed interval. Now, let us take any closed interval a b which is a subset of D. Then its image which is f of a b. So, that means it is the set of all values f of x such that x varies over the closed interval a b. So, recall that this is denoted by f of a b. So, this f of a b will be equal to a closed bounded interval which is C D for some c less than or equal to d. If f is a constant function, of course, you may get equal to. So, here we will take equal to sign also a possibility. This is what we mean by the continuous image of a closed bounded interval, that is f of a b is a closed boundary interval which is C D, where f is assumed to be continuous. This is the main theorem. So, this may not happen if f is not continuous, or you do not start with a closed boundary interval. Even if f is continuous, you may not reach a similar interval there. Many things can happen. So, we will not prove this, but this is what we are going to use. And usually in calculus, we do not define functions over any arbitrary subsets to R. We do not concern them usually. So, again there is a reformulation of this theorem, where we start directly that f is defined on the closed interval a b. So, that is how it is usually mentioned. Let f from a b to R be continuous. Then its range, which is f of a b, is equal to C D for some c less than or equal to d. That is a very convenient form to use. Okay. So, once we understand this, we can go to the next theorem, which is will follow from this exactly. So, which is called the extreme value theorem. Let us try to understand what it says. It says that first of all, if f from a b to R is continuous, then there is a number which is minimum of all f x x belongs to a b. And now that follows, because f of a b, this is really f of a b, this one, that is equal to C D. So, C is that minimum, then minimum of this exists, that is really C. Similarly, D will be the maximum. So, maximum also exists, maximum of the range. And once it is continuous, then we say f of a b equal to C D. So, that means there is one point on the left side a b such that f of that point equal to C. So, which we will say that f of alpha and f of beta, one is maximum, one gives the maximum value, the other gives the minimum value, right. So, this happens, that is a continuous function achieves its maximum and minimum values. Of course, this way it is informal, but that is how we remember most of the things, by looking at them informally. Okay. So, that is why this is called extreme value theorem, that a continuous function achieves its extreme values, minimum and maximum values. So, that of course follows from the mother theorem. Okay. So, there is one more important thing which is called intermediate value theorem. What it says, suppose f is defined over a closed boundary interval taking real values and it is continuous. Now, f of a and f of b are certain values in R. You take any point in between f of a and f of b, say it is y0. Look at the picture. Then it says that there exists a point C in a b such that f of c equal to y0. Extreme value theorem says that C and D, the minimum and maximum of f in the range, are achieved. That is, there are some points alpha and beta where f of alpha, f of beta gives us the minimum and maximum. But here it says, it is going a bit further, it says that between f and fb, you choose any number, that is also achieved. That is, there is a point C in AB such that f of c equal to y0. You can see geometrically why it is so. F of a is somewhere here, f of b is somewhere here. So, in between is any y0 if we take, and we just take a horizontal line, it will cross the curve somewhere. That gives us the point. Of course, it does not say there is a unique one, right. Suppose it goes on coming down and again, and you draw one line, it can hit at many of the points. So, there can be many points, but there exists one, that is what. On the other hand, if it is not continuous, for example, like this may not happen in the second picture. So, there is a point, if I choose between 2 and 3 something, say 2.5, then draw that horizontal line, it will never hit the curve anywhere. So, there is no point in the x axis such that f of x is equal to 2.5, but that is between 2 and 3, right. So, that is what intermediate value theorem says. Extreme value theorem, two extremes. Intermediate value theorem says even in between points are also achieved. Again, this follows from the mother theorem, main theorem, that f of ab equal to c comma d. So, something between minimum and maximum, if you choose any 2 points, those 2 points also are achieved. That is what extreme value theorem says. But here what we do? We take f of ab. So, consider in particular f a and f b. These are 2 numbers. Now, if you choose any number between f a and f b, that is your y0, choose y0 between f a and f b, that also lies between the minimum and the maximum of f of x. Therefore, there is a point where it is achieved. That also follows from the earlier one. Okay, there are nice applications of this. We will see soon. We will see one more result which comes from this, which is called the sign preserving theorem. This is also very important theorem. It gives an idea of what continuity in a small neighborhood means. So, suppose f is a continuous function, we will start with an interior point c of d. For example, if f is defined on the closed interval a b, then c will not be the end points a and b, it is something else in between a and b, but not equal to a and b. So, once you say it is an interior point, recall it is an interior point means there is a neighborhood of that point which is contained inside D. That is why it is called an interior point. Always there is a neighborhood around it which is a subset of D. So, that means f will be defined on that neighborhood at least. Okay. So, suppose f of c is greater than 0, something like here c is greater than 0. Look at this, forget the earlier legend. Suppose it is a continuous function and c is there, f of c is bigger than 0. Then it says there is a neighborhood c minus delta to c plus delta such that on the whole neighborhood the function remains positive. So, I can choose say here something between this, in fact I can choose bigger, but suppose the function comes down to like this, somewhere, then I cannot choose my delta to be so big, because f of this will be negative. So, it says there exists a neighborhood where f remains negative. How does it follow? Why does it follow intuitively? Let us see. Suppose it is remaining positive and it does not happen that whatever neighborhood you take around that point, you will find some negative point or 0. In fact, if you get a negative point, then because of intermediate value theorem, 0 is also achieved. So, 0 is there somewhere. That means, you have the function, you have C, you take any neighborhood. So, you will find there is a point, or in fact, there is a point where it is 0, or it is, in fact, if you take any point, it will be 0 or negative, right. The contradiction of this, the contrary of this we are assuming, because this is the result to happen. If it does not happen, then you take C, any neighborhood of this, around this you take any point, there it is either less than 0 or equal to 0. Okay. So, now here it is positive and here it is negative or it is equal to 0. Then by intermediate value theorem, all these values should have been achieved, right. Between 0 and that, there is a point where it is 0. So, once all these values, say this is, there is no 0 elsewhere here, we can always choose one point, after that there is 0 is never taken, otherwise everywhere it is 0, and directly from that point it will fall to 0, it will not be continuous. That is our intuitive feeling. And of course, we can prove also, it is easy to prove. Instead of using this intermediate value theorem, it is more fundamental. So, let us give a proof even, does not matter. Let f from D to R be continuous at an interior point C. If f c is greater than 0, then there exists a neighborhood such that f x is greater than 0 in that neighborhood. So, what we do, suppose f of c is bigger than 0. Okay. So, it looks something like this, c and f of c is bigger than 0 somewhere here. Then what we do? We start with something which is difference between 0 and this, that height we will take, that we will take as epsilon. So, that we will get a corresponding neighborhood where this will lie between f of x minus f c will lie between that epsilon, right. So, let us choose something less than that, so less than half of that even. So, we will see what is the advantage of choosing that. Suppose f c is bigger than 0. Now, let us take epsilon equal to f c by 2, difference from 0 to f of c, f c by 2. Now, for this epsilon, since f is continuous, there is a delta greater than 0 such that whenever x belongs to c minus delta to c plus delta, this neighborhood, we have f x and f c difference should be less than epsilon, which is f c by 2. Now, if you rewrite this as an inequality, this says f c minus f c by 2 less than f x less than f c plus f c by 2, which gives you f c by 2 less than f x less than 3 f c by 2, right. So, there is a neighborhood which is c minus delta to c plus delta such that for each point in that neighborhood, f of x lies between f c by 2 to 3 f c by 2, but f c by 2 is greater than 0, therefore, f x is greater than 0. That is, for each x in the neighborhood c minus delta to c plus delta, our f of x is bigger than 0, and that is the proof. Okay. So, now this says about the interior point. C is an interior point, that means around C there is a neighborhood which is contained inside D. Suppose it is not an interior point, but we are concerned about intervals. D is an interval and C is one of the endpoints of D, right. So, suppose something like AP is from AB to R, it is also continuous at x equal to A, and FA is greater than 0. Then what can we say about the neighborhood? We can't say there is a neighborhood around A which is inside it, but we have only a right neighborhood which is contained inside the domain which is closed A open B. So, in that case really the result comes to this, there is a delta greater than 0 such that f x remains positive in the neighborhood A to A plus delta. That of course is covered in this same proof, because by definition when you say continuous at a left hand point, we will have a right neighborhood only where these things happen. Therefore, the same proof we will little modification. Instead of this, we will be taking here c to c plus delta and continue the proof. Similarly, when it is the right end point, that is f is from a b to r is continuous at x equal to b, and you know that f of b equal to 0, then we have a left neighborhood b minus delta to b where f of x remains positive. Okay. So, I think this is understood, but then this is about positive. So, if you have negative f of x, say f of c is less than 0, then of course, you will get a neighborhood where f of c remains negative. The proof of course is easy because you consider minus f instead of f throughout. The same proof will work. So, that is what we give a comment that similar statement hold when you replace this greater than with less than. If it is negative at a point and it is continuous, then it will remain negative in a neighborhood of it. In fact, you can think of it is bigger than some number k, right? F of c is bigger than k. Then there is a neighborhood of c where f of x remains bigger than k. Fine. Also for less than. So, these are our main results. We have the extreme value theorem, intermediate value theorem, and the sign preserving property of continuous functions in a neighborhood. So, let us give some example where we can do this. So, this is our first example. We have a b c d is a square. So, that means it is something like this. Let us name them following some order. A b c d is a square. Draw two curves. So, what are the curves? They are assumed to be graphs of continuous functions. That means, you do not do like this. You should not do like this. They cannot come back to this side. Is that okay? That will not be happening there. Okay. Suppose we start with a curve which is assumed to be a continuous function. So, then in that case, what will happen? Okay. So, let us do it this way, rather we take this way. We have the square, say a b c d, and what happens? We are trying to draw two curves which are assumed to be graphs of continuous functions lying inside a b c d. They will not go away. One joining a and c, another joining b and d. Suppose a and c, so it is something like this, and another is something like this, b and d. They lie inside. So, obviously, what is asked is to show that two curves intersect somewhere inside the square. It is intuitively very obvious, but we require proof. Well, so what do we do? Let us write a to be the origin. It is done the other way. We take this to be a, and this to be b, this to be c, and this to be d. Okay. So, this point let us write 0 0, b let us write as 1 0, c as 1 1, and d as 0 1, taking this as the y axis, this is the x axis. Okay. So, now f is a function and g is also a function. So, both are defined from 0 1 to 0 1. Okay. Are they defined from 0 1 to 0 1? The one function is like this, the other function is like this. So, one is defined from this to this. So, their height remains between 0 and 1, right, both the heights. So, f and g are functions from closed interval 0 1 to closed interval 0 1. That is obvious. Now, what is f of 0? F of 0 equal to 0 here. This is our f and this is our g. So, f of 0 equal to 0 and f of 1 equal to 1. G of 0 equal to 1 and g of 1 equal to 0. This is what we get. Both are continuous functions. I think this much information is enough. We will not need the picture after this. So, what happens is we define another function h of x, which is f x minus g x. We know that this is continuous. because of algebra of continuous functions. This is continuous from where? From 0 1 to what is the range? So, range will be f 0 and g 0 is 1. So, minus 1 to 1, right, range is minus 1 to 1. So, it is a function, h is a function from 0 1 to minus 1 to 1, and what we get? h 0 equal to minus 1, h 1 equal to 1. Now, use intermediate value theorem. Between minus 1 to 1, 0 lies. So, there is one number here x such that h of x equal to 0, right. So, there is a point C such that h of c equal to 0. And what is the meaning of h of c? It is really f c minus g c. So, f c minus g c equal to 0 or f c equal to g c, and that is the meaning of the curves intersect. Okay. So, this is an application of intermediate value theorem. Let us take another example. So, here it is claimed that every polynomial of odd degree has a real root. We want to show that yes, it is correct. If you take any polynomial of odd degree, it will have a real root. All polynomials may not have real roots, right. So, this says only about odd degree polynomials, like x square plus 1 equal to 0, it does not have any real root. However, if you take a cubic, then there exists at least one real root. So, how do we proceed? We start with a polynomial, say p x equal to this. Now, here we have made the coefficient of x to the power n as 1. There is no loss in generality, because anyway we are interested in finding a root. So, if this also this has a root, then the general one also will have a root, because just dividing by n, it is of degree n. So, n is non-zero. So, that really does not matter. So, let us assume that p x is in this form, where it is coefficient of x to the power n is 1 and n is odd. Okay. Now, if I take limit of this as x goes to infinity, what happens there? X goes to minus infinity of p x. So, when you take p x, it is x to the power n plus a n minus 1, x to the power n minus 1 and so on. Okay. So, as x goes to minus infinity, really I take x bigger than these coefficients, a 0 plus a 1 plus all mod a n minus 1. Then this term x to the power n will dominate all the other terms. Okay. So, when x goes to minus infinity, this polynomial can be made, its value can be made smaller than any negative number. So, it say that limit x goes to minus infinity p x is minus infinity, because n is odd. So, this becomes minus infinity. Had it been even, it would have become infinity. Okay. Now, similarly, if I take limit of p x goes to infinity, that becomes infinity, okay, because x goes to infinity. So, this dominates again, this term only tells you what is the result. Okay. So, now let us see what is the meaning of this. Limit x goes to minus infinity p x equal to minus infinity. It means there exists a point negative number a such that p of a is less than minus 1. In fact, it means that p, the functional value p of something, can be made smaller than any negative number you give me. That is, you give me something, say minus 100, then I can get one x such that p of x is less than minus 100. So, here in particular we say there exists a number a negative such that p of a is less than minus 1. Similarly, when we have limit p x equal to infinity, means there exists a number b, say positive, such that p of b is bigger than 1. So, now p of x is a continuous function. So, we can just restrict it to our domain a b instead of taking the whole real number. Now, there the function is p x, f of x equal to p of x, this polynomial, and we see p of a is some number less than minus 1, p of b is some number bigger than 1. Therefore, by intermediate value theorem, since 0 lies between minus 1 to 1, there exists one point c such that p of c equal to 0. That is what we wanted, right. that P of C must be equal to 0 for some C. It is an odd degree polynomial, it has a real root, and that is the proof.